Atoms come together to form molecules because the chemical bonds that connect them bring the system to a lower energy. They are interactions between atoms that are thermodynamically favorable. And if we are looking at covalent bonds, the energy contained within the bond will depend on a few factors. First, the types of atoms that are participating in the bond. Then, the length of the bond, which can depend on whether it is a single, double, or triple bond. These different types of bonds can be quantified when we measure the amount of energy released when we break the bonds. This is called the bond dissociation energy. So first, we have to consider which elements are participating in the bond. A hydrogen-hydrogen bond will store a certain amount of energy, as will a carbon-hydrogen bond, a carbon-carbon bond, a carbon-oxygen bond, or any other type of bond. And for the most part, the more polar the bond is, the more energy it will store. Look at this comprehensive list of bond energies. For the single covalent bonds, some of the strongest are ones like HF and HO. That's partially because of the electronegativity of some of these elements, but also because of bond length, given the smaller size of the atoms in the second period. We will notice that these double and triple bonds can store even more energy. For a particular set of atoms, a single bond will be the weakest, followed by a double bond, and then a triple bond will be the strongest. We can see this by looking at the potential bonds formed between two carbon atoms, or two nitrogen atoms. This also has a correlation with bond length, because a single bond, or a sigma bond, will be the longest and therefore the weakest. Adding a pi bond to make a double bond, like this molecule of C2H4, will result in greater orbital overlap, which causes the interatomic distance to contract, making a shorter, stronger bond. And adding another pi bond to form a triple bond would generate a still shorter and stronger bond. We can use these values to find the bond dissociation energy of a compound. We simply add up the individual covalent bonds in the molecule. Take this one, for example. Here we have one carbon-carbon bond and 6 carbon-hydrogen bonds. So we just multiply by the values in the table. Then add those up, and this will be the bond dissociation energy for a mole of ethane. If we want to find the change in enthalpy of a reaction, we can simply take the energy of the bonds broken and subtract from that the energy of the bonds that are formed. The difference must be the change in energy of the reaction. And to summarize, we know that bond strength increases as bond length decreases, and as more bonds are added between the two atoms. This is how we can gauge covalent bond strength.